Have you ever noticed how, like, some piece of information or maybe a new trend suddenly just explodes through your social circle?
Oh, yeah, definitely. Or how maybe a new restaurant gets discovered. Not really through ads, but just people talking.
Exactly. It all seems to come down to connections, doesn't it? These sort of invisible threads that link people, places, ideas.
Even proteins in a cell. It's fascinating. What if there was, a powerful scientific way to look at these very connections, no matter how complex they seem?
Well, that's precisely what we're diving into today.
Indeed. From the incredibly intricate neural networks in your brain letting you think and feel,
Right.
to the huge, sprawling structure of the internet, delivering this very deep dive to you right now. And other than, really, at some basic level, can be seen as a network. It's everywhere. A totally fresh perspective.
Yeah.
Often on systems we thought we knew.
And that's the field. Network science. It's not just drawing lines and dots, is it? It's this amazing interdisciplinary field helping us map, measure, and really make sense of the hidden structures governing so much. So today we're going to unpack the core ideas, discover some surprising, really profound links to classical physics.
Which is quite unexpected for many.
Totally. And even show you how you can actually start exploring these complex systems yourself with tools that are pretty accessible.
Absolutely. Our deep dive today, it's built on some really solid sources. We've got lecture materials from the 21st Kias APCTP Winter School on Statistical Physics by Sang-Hoon Lee.
Okay.
Some key research papers by Lee, Park, and Newman pioneers in the field, and a great textbook on network science, too.
So our mission here is to pull out the most important insights, help you get really well informed about this powerful way of thinking about complexity.
Exactly.
Okay, let's unpack this. When you really strip it all down, a network is surprisingly simple at its core, isn't it?
It is, fundamentally.
We call the individual things nodes or vertices. So that could be people, computers, neurons, cities, whatever.
Right, the entities.
And then you have the links or edges. Those are the connections between them.
Simple as that.
Like a friendship is a link between two people nodes, or an email between two computer nodes. It's all about who or what connects to what.
And right away, a really crucial idea pops up. Degree.
Degree.
The degree of a node is simply the number of links attached to it. Super basic, but vital.
So like how many friends someone has on Facebook or how many roads connect to a city.
Exactly. Now, in what we call an undirected network, where links are two-way, like a handshake or that mutual friendship, just the total count. But sometimes connections are one-way, right?
Like following someone on social media, but they don't follow you back, or one paper citing another.
Precisely. We call those directed networks. And there, we often distinguish in degree how many links point to the node from out degree, how many links point away from it.
Okay. So in degree might show popularity or influence, while out degree shows activity.
Sort of, yeah. Understanding a node's degree gives you an immediate sense of its role or prominence in the network.
And this idea of degree, it's not new, right? This connects back to some really foundational math history.
Oh, absolutely. Way back. The importance of degree actually dates back to the 18th century and the brilliant mathematician Leonhard Euler.
The Königsberg Bridge problem. I remember this one.
That's the one. You've got this city split by a river, two big islands, 7 bridges connecting everything up.
And the puzzle was, could you take a walk, cross every single bridge exactly once, and end up back where you started?
Exactly. Sounds like a fun little riddle, but Euler's approach was, well, revolutionary for its time. It basically founded graph theory.
How did degree play into it?
It was everything. Euler's genius was simplifying it. He saw each landmass as a node, each bridge as a link.
Okay.
And he figured out that such a path, we now call it an Eulerian path, is only possible if the number of nodes with an odd degree, meaning an odd number of bridges, is either 0 or exactly 2.
Only 0 or 2 nodes with an odd number of connections.
Right. In Königsberg, all 4 landmasses had an odd number of bridges. So Euler proved mathematically it was impossible. No such walk existed.
Wow. So just by counting connections, he solved it. That really shows how fundamental degree is. It's not just a number. It dictates what's possible in the network.
It truly does.
Yeah.
It's a predictor of behavior.
So, okay, we have nodes, links, degree, but the links themselves can be different, right? You mentioned directed versus undirected.
Yes. Undirected, like, say, a partnership where it's mutual. Directed, like maybe a teacher-student relationship where information flow is mainly one way.
And what about weights? Sometimes a connection is stronger than another.
Great point. Links can be unweighted. They just exist, yes or no. Or they can be weighted.
Meaning they have a value, like the strength of the friendship or the number of emails exchanged.
Exactly. Or maybe the amount of traffic on a road link between two city nodes. That weight adds a whole new layer of richness. A simple link tells you two people know each other. A weighted link might tell you how close they are.
That makes sense. And when we look at real networks, are they usually dense with tons of connections or something else?
Mostly something else. Real-world networks are almost always sparse.
Sparse, meaning not many connections compared to how many could exist.
Precisely. Think about a complete network where every single node is linked to every other node.
That sounds like chaos, just connections everywhere.
It would be incredibly dense, yeah. Mostly a theoretical idea. In reality, networks are much more selective. Like the Facebook network at Northwestern University studied in our sources. Its density was about 0.0009.
Less than 1% of all possible friendships actually existed.
Right. Or think about actors on IMDb linked, if they're co-stars. That density is even tinier, like 0.000003.
Wow. Okay, so real networks are vast, but the connections are actually quite selective and few, relatively speaking.
Exactly. It's about finding those crucial connections in a sea of potential but non-existent ones.
Okay, so understanding these basics, nodes, links, degree, sparsity, that's one thing. But how do we actually see these massive, sparse, real-world networks? I mean, gathering complete data on, say, all social interactions in a city or the entire internet. That seems impossible.
It usually is impossible, or at least impractical. And that's where sampling comes in.
Yeah.
It's absolutely essential, but also quite tricky.
Because you can't see the whole picture, you have to take a snapshot.
Exactly. But like trying to understand a whole rainforest by just looking at one small square, your snapshot might not represent the whole thing accurately. It brings up big questions about accuracy and, crucially, bias.
So how do researchers typically do this sampling? The sources mentioned a few ways.
Yeah, there are some basic methods. One is node sampling.
Yeah.
You just randomly pick some nodes, say people, and see who they're connected to.
Okay.
Then there's link sampling. You randomly pick existing connections and look at the nodes on either end.
Right.
And the third is snowball sampling.
Oh.
Which does sound kind of fun.
How does that work?
You start with one node, or a few. Then you find all their direct connections, their neighbors. Then you find all of their neighbors, and so on, adding layers outward. Like a snowball rolling downhill, gathering more snow.
Okay, that makes intuitive sense. But you mentioned bias. How does the way you sample affect what you find?
This is where it gets fascinating and a bit problematic. Each method can give you a skewed view of the network.
Skewed how?
Well, as Sang-Hoon Lee and colleagues showed back in 2006, things you want to measure about the network shape its topology. Like the average distance between nodes, how clustered it is, which nodes are most central. These can come out looking quite different depending on how you sampled.
So using snowball sampling might give you a different average path length than random node sampling.
Potentially, yes.
Yeah.
Significantly different even. This isn't just a minor detail. It's a major challenge if you want to accurately understand the real system you're modeling.
Okay, let me make sure I get this. If you, say, consistently underestimate the average path length, how many steps it takes to get between nodes on average? Why does that matter practically?
Excellent question. That's the so what.
Oh.
If you think the path length is shorter than it is, you might assume information or maybe a disease spreads much faster than it really does.
So a public health campaign designed to go viral might fail if your model's path length is wrong.
Exactly. It might fizzle out. Or consider the clustering coefficient that tells you how much your neighbors are also connected to each other. Like, are your friends also friends with each other?
Okay, tight-knit groups.
Right. If your sampling method underestimates that clustering, you might miss how strong and resilient local communities are. You might design interventions that don't work, or misjudge how robust a supply chain really is.
So it's like trying to map a forest. If you only sample trees near the river, a biased node sample, you might think the whole forest loves water.
Perfect analogy.
Or if you only look at the well-trodden paths, a biased link sample, you miss the wild, untouched areas. Lee's paper really stressed needing ways to correct for this, right? To avoid over or underestimating.
Absolutely. Because if your data, your sample, is fundamentally flawed, then no matter how fancy your analysis is, your conclusions could be wrong, leading to bad decisions.
Yeah, that makes sense. The challenge is making sure your sample truly reflects the whole network you can't see.
It really is. And this difficulty, this inherent incompleteness in our observations, raises a huge question. How do we build reliable theories? How do we model these things generally if our data is potentially biased?
That's a really good transition because we've seen how messy real-world data can be, how sampling can introduce bias. So how do we move beyond that to build more robust theoretical models? And you mentioned earlier the answer, surprisingly, comes from physics.
It does, remarkably. From statistical physics, to be precise. It seems like a leap, but it provides an incredibly powerful framework for exactly this kind of problem, dealing with systems where you have incomplete information but want to understand general behavior.
How does that work? How does physics connect to networks?
Well, the key insight is how network science thinks about a random graph. It's not just one specific network drawn randomly.
No.
No. It's conceptualized as a statistical ensemble. Imagine the collection of all possible graphs that could exist under certain conditions, with each specific graph having some probability of actually occurring.
Okay, so not just one random network, but the whole space of possible random networks, each with a likelihood.
Exactly. And this idea is basically identical to a foundational concept in statistical mechanics.
Statistical mechanics, like
Yeah.
thermodynamics, predicting how gases behave.
Precisely that. Think back to Ludwig Boltzmann in the 1870s. He explained that a statistical ensemble in physics is the complete set of all possible states a system could be in.
All the ways the atoms could be arranged and moving.
And he showed that the statistical weight or probability of each state depends on its energy. You often see it written as WB is proportional to E to the minus beta E.
Oh, wait, E. Right. That pops up a lot. In plain English, what's the core idea there?
It basically means states with lower energy are exponentially more likely to occur than states with higher energy.
Like a ball rolling downhill finds the lowest point.
Kind of, yeah. It gives a statistical picture of the system's most probable configurations, letting us predict overall properties like temperature or pressure without tracking every single particle.
And this idea came from?
Well, James Clerk Maxwell first used statistical for thermodynamics in 1871, seeing it was about probabilities. Then Josiah Willard Gibbs coined statistical mechanics in 1884. This whole framework is incredibly powerful.
Okay, so that's the physics side. How does this ensemble idea, this Boltzmann probability, apply back to networks? What's the equivalent of energy for a social network?
That's the brilliant connection. We have a direct analog. Exponential random graph models, or ERGMs.
ERGMs, okay.
Think of ERGMs as the Boltzmann distribution, but for graphs. They aim to give the best prediction of network properties subject to the constraints imposed by a given set of observations.
How? By doing what?
By maximizing entropy. Just like the Boltzmann distribution describes the most likely arrangement of particles given their total energy, ERGMs describe the most likely network structure given certain things you have observed.
So if I've measured, say, the total number of links in my sampled network and maybe the number of triangles,
Right, those are your constraints.
ERGMs can tell me the most probable entire network structure that would produce those features while making the fewest extra assumptions.
Exactly. It's about being maximally unbiased given the information you possess. Maximize entropy means you assume nothing beyond what you've observed. It gives the most robust, least presumptive prediction of the overall structure.
That sounds incredibly powerful, like building a model that respects your data but doesn't overinterpret it.
Precisely. And the work by Jillian Park and M.E.J. Newman in 2004 was really key in explicitly applying these statistical mechanics techniques to networks. They showed how these physics principles could eliminate network structure, letting us build theories that go beyond potentially flawed empirical data.
It's just amazing that the math describing gas particles or magnets also helps understand social groups or the internet.
It highlights the deep underlying mathematical similarities in complex systems. It's not just an analogy, it's a genuine theoretical connection.
Okay, now all this talk of nodes, links, statistical ensembles, Boltzmann, it might sound, pretty intimidating, maybe just for academics.
It can sound that way, sure. But the really good news is that practical tools have made network analysis way more accessible than you might think.
Yeah, you don't need a supercomputer or that physics PhD.
Definitely not to get started. Our sources point to a fantastic tool, very widely used, NetworkX. It's a Python package.
NetworkX. Okay, I've heard of Python.
It's essentially a library that lets you create, manipulate, and study networks easily. It handles all sorts of simple graphs, complex ones, directed, undirected, weighted, and it's open source.
Open source meaning free to use.
Free to use, free to modify. It really helps democratize network analysis.
So what can you actually do with it? How hard is it to start?
Surprisingly easy. A few lines of Python code get you going. Like to create a basic undirected graph like friendships, you just type nix.graph.
Nix.graph, got it.
If you need direction, like emails, it's nx.daver. Adding nodes is simple. G add node, Zoil1, adding links. G add edge 1 and 2.
Okay, that does sound straightforward.
And a nice feature if you add an edge between nodes 1 and 2, but maybe node 2 wasn't explicitly added first. NetworkX just creates it for you automatically. Super handy when reading data.
Ah, that is convenient. Can it build whole networks for you, like standard types?
Yes. Beyond adding piece by piece, it has generators for common theoretical networks. Useful for testing ideas. You can make an nx.pathgraph, just a line of nodes.
Like a chain.
Or nx.stargraph, one central node connected to everything else.
A hub and spokes.
Exactly. Even things like nx.completeByPartygraph.
Whoa, bipartite. What's that?
That's a network with two distinct sets of nodes, say set A and set B. Connections only go between set A and set B. No connectors within A, none within B.
Oh, like people and events they attended. People connect to events, but not directly to other people in that context.
Perfect example. Or bees and flowers and pollination. Bees connect to flowers, flowers connect back, but bees don't connect to bees or flowers to flowers through that specific interaction.
Okay, cool. So you've built your network. What can you find out about it using NetworkX?
Loads. You can easily get the degree of any node. G degree node.
We know degree is important.
Crucial. For directed graphs, you can get D in degree node and D out degree node separately.
To see inflows and outflows.
And if your network is weighted, remember, links have values.
Yeah, like connection strength.
You can calculate the strength of a node using W degree. Node weight. That sums up the weights of all its connections. A really powerful measure of total influence or activity.
Okay, this is making sense. Now, you mentioned real networks can be huge, but sparse. Does NetworkX handle that efficiently? How does it store the data?
That's a really important practical point.
Yeah.
There's a traditional way, mathematically nice, called the adjacency matrix.
Matrix, like a grid.
Exactly. A square grid where rows and columns are nodes. A one in cell, Ij, means node I is connected to node J. If 0 means they're not.
Seems logical.
It is, for theory. But think about a sparse network. Millions of nodes, but few connections. That matrix would be enormous, mostly filled with zeros. Very wasteful of computer memory. Needs n squared memory, where n is nodes.
So for big sparse networks, that's bad.
Very bad. You run out of memory fast.
Yeah.
So NetworkX and other tools usually use more efficient methods for sparse networks, like adjacency lists.
Adjacency list.
Instead of a huge grid, for each node, you just store a list of its actual neighbors. Much more compact if connections are few.
Just list who you're actually connected to.
Right. Or even simpler, an edge list. Just a list of all the connections that exist, like pairs, node 1, node 2, maybe with a weight, node 1, node 2, weight. Memory use scales with the number of links, not nodes squared. Much better for real data.
Makes sense. Store what's there, not all the empty space. And can you see the network, visualize it?
Yes. Visualization is key for understanding structure. NetworkX works well with other Python libraries like matplotlib.pyplot to actually draw the graphs.
So you can see the patterns.
Exactly. You can use different layout algorithms like a spring layout that tries to position nodes based on their connections, pulling connected nodes together, pushing others apart. It can reveal clusters, central nodes, bridges, things hard to spot in raw data.
Okay, this sounds genuinely doable. If someone listening wants to try this, where should they look?
Oh, there are tons of great resources. The official NetworkX documentation itself is excellent, very clear, lots of examples.
Right.
You can find countless tutorials online, often as Jupyter notebooks, which mix code and explanation. Google Colab lets you run Python and NetworkX right in your web browser, no setup needed.
Perfect for beginners.
Absolutely. And for deeper dives, textbooks like A First Course in Network Science offer great hands-on guidance. It really is a field you could jump into and start exploring.
What an incredible journey today. We really did a deep dive into network science. We started with those basic bits nodes, links, and saw how crucial degree is, even way back with Euler and the Königsberg bridges.
Such a great historical anchor.
Then we got into the tricky business of actually observing real networks, the whole sampling issue, and how different methods can create bias.
Which has real consequences for how accurately we understand things.
Definitely. And then we bridged over to that unexpected connection with statistical physics.
Yes, seeing random graphs as statistical ensembles, just like Boltzmann did for physical systems.
Yeah.
That's profound.
And how ERGMs use that idea, maximizing entropy to make the best predictions from limited data, building on work by Park and Newman.
It gives us a solid theoretical footing.
And finally, we made it practical. We saw how tools like NetworkX make this accessible. You can actually build graphs, analyze them, visualize them.
And handle large, sparse data efficiently using things like adjacency lists instead of just matrices.
Right. Yeah. It puts these powerful ideas within reach.
Ultimately, what I hope comes across is just how universal and interdisciplinary network science is. It's more than tools. It's really a lens, a language for understanding complexity.
Yeah.
Whether that's in biology, sociology, computer science, physics, it applies everywhere.
So as we wrap up, what does this all mean for you listening right now? Here's maybe a final thought to chew on. Take a moment later today. Think about some system in your own life or your work. Could be your project team, how customers move through your business, maybe even topics in something you're learning. Now imagine mapping its connections. Apply that network science perspective, even just mentally. Who connects to whom? Where does information flow? What might that reveal?
What surprising insights might pop out that were hidden before?
Exactly. What patterns could you uncover? And how might knowing that change how you approach things? The world really is a network. What might you discover by starting to see those connections? Hello, curious minds, and welcome to The Deep Dive.
Great to be here.
Today, we're plunging into a really fascinating stack of sources. We've got university lecture materials, some cutting-edge research papers.
A real mix.
Yeah, all focused on these, well, hidden architectures, the structures that govern pretty much everything, right? From our social circles to the whole internet.
Absolutely.
And our mission, as always, is to pull out those key nuggets of knowledge, the sort of aha moments, to help you quickly get up to speed on the surprising patterns beneath the surface of our connected world.
And what's truly remarkable, I think, is just how universal these network structures are.
Right.
I mean, understanding them lets us predict things like behavior, influence, even vulnerabilities.
Across totally different systems.
Exactly. Friend groups, disease spread, online information flow. It's the same fundamental principles at play. It's a really powerful lens.
Okay, so let's unpack this. Let's start with a concept many of us kind of get intuitively. Assortativity. You've heard the saying, birds of a feather flock together. Turns out that's not just, an old saying. It's real network science.
It absolutely is. Assortativity, well, it describes this tendency for nodes. Could be people, websites, proteins, anything really, with similar attributes to connect.
So, like, connects to like.
Pretty much. Yeah. Think about a social network. You'd expect people with shared interests, maybe similar ages or backgrounds, to link up, right?
Yeah, that makes sense.
If you visualize it, you'd see these groups, maybe nodes of the same color, mostly linking to other nodes of that same color, forms these tight clusters.
A natural grouping.
Based on shared traits, yeah, or similar roles in the network.
And we can get even more specific, right? With something called degree assortativity.
That's right.
That zeroes in on how connected the nodes are. Like, do the popular nodes, the ones with tons of connections?
The high-degree nodes, we call them.
Right. Do they tend to link up with other popular nodes, or is it the opposite?
And that distinction is really crucial. Tells us a lot about the network overall architecture.
How so?
Well, in many social networks, for instance, we see strong assortativity by degree.
Okay.
Think about it. Popular people, the ones with lots of friends or followers, they often know other popular people.
Creates like a cool kids club.
Sort of.
Yeah.
It creates what's sometimes called a core periphery structure. You get this densely connected core of popular individuals, and then less connected folks are kind of orbiting around them.
So like a busy city center with big roads connecting to other big roads. But you're saying that's not the whole story.
Not at all. If we look at, say, technological networks or biological ones, think the World Wide Web, the internet's actual infrastructure, even food webs.
Yeah.
They tend to be disassortative.
Dissociative. Okay. Opposite.
Right.
Yeah.
Here, the hubs, the high-degree nodes, they're more likely to connect to lots of low-degree nodes.
So the big hubs connect out to the little guys.
Exactly. Instead of hubs linking to other hubs, you get this star-like structure, a hub in the middle connecting out to many less connected points.
And that's efficient for spreading stuff.
Incredibly efficient for spreading information or resources from that central point.
Though, there's always a but.
Yeah. It also means those hubs become really critical single points of failure. Take out the hub, you disconnect a lot of nodes.
Wow. Okay. And this whole idea of similar things connecting, it has, well, the sources mention a dark side of homophily.
Homophily just being that tendency for similar things to connect.
Right. And the dark side.
On social media, this can easily lead to what we now call echo chambers or filter bubbles.
We hear those terms all the time.
And that's where the real-world impact hits hard. Inside these echo chambers, you're mostly seeing info and opinions that just reinforce what you already believe.
Cuts you off from other views.
Exactly. It narrows your perspective. And as the source material warns, it can make us, well, alarmingly vulnerable to manipulation. Think misinformation campaigns, social bots.
Because you're not getting that counter-information.
Precisely. It stifles critical thinking. It limits your exposure to diverse viewpoints. It's a big problem.
It really is powerful how a network principle can directly impact public discourse like that. Okay, for the quant fans out there, how do we measure this? Assortativity.
We can use a statistical tool, the Pearson correlation coefficient.
Okay.
It gives us a number, basically, from -1 to +1.
Simple enough.
+1 means perfectly assortative. High degree only connects to high degree, low to low. -1 is perfectly disassortative. High only connects to low.
And reality is somewhere in between.
Usually, yeah.
Yeah.
And that number tells you a lot about the network's bias towards, similarity or difference in connections.
Got it. So, okay, we understand who's connecting to who, whether it's birds of a feather or hubs and spokes. The next big question for navigating any network is, how do we get from A to B? Which brings us to paths and distances.
Absolutely fundamental. The whole idea of a path is the basis for defining distance. It's just a sequence of connected links.
Simple.
Yeah, but one of the earliest problems that really kicked off graph theory and network science was the Königsberg Bridge problem back in the 18th century.
Oh, I think I've heard of this one. 7 bridges.
That's the one?
Yeah.
The challenge was, could you walk through the city and cross each bridge exactly once?
Just a fun puzzle, or more to it.
Well, Leonhard Euler proved it was impossible, but in doing so, he developed the concept of an Eulerian path, traversing every edge exactly once.
Ah.
And it's only possible under specific conditions related to nodes with odd numbers of connections. But the key thing for us, it showed the power of abstracting connections into a network and asking about navigability.
Yeah.
It's the ancestor of, what's the best delivery route?
Or can I reach everywhere in this system?
Exactly.
And when we think shortest path, we usually mean fewest steps, right? Fewest links.
Often, yes. But in many real networks, those links have weights or costs.
Like?
Think travel time on roads, cost of data transfer, maybe the energy needed for a biological reaction.
Right. So it's not just the number of hops.
Exactly. So the shortest path might actually take more links, but have a lower total cost when you add up those weights.
It's like taking 3 short flights instead of 2 long ones with a huge layover.
Perfect example. The 3-flight route has more links, but it's shorter in terms of total time.
So how do we find these shortest paths, especially in big, complicated networks?
The key algorithm is breadth first search, or BFS.
BFS.
It's really systematic. It explores the network layer by layer. Starts at a source node, then visits all its immediate neighbors, then their neighbors, and so on, like ripples spreading out.
Like wave.
Okay. And by tracking the shortest distance found so far to each node, it efficiently maps out the shortest path tree to everything reachable.
So it's behind things like GPS navigation.
Absolutely. GPS, social media friends suggestions. It's fundamental.
Yeah.
And we can use tools like the NetworkX library in Python to run these algorithms on real data very quickly.
Very cool. Okay, so if paths tell us how to get around, then connectedness tells us if we can get around at all.
Right.
Like, are we all on one big continent, or are there isolated islands?
That's a great analogy. A network is connected if there's some path between any 2 nodes.
Fully connected.
If not, it's disconnected, meaning it's made up of multiple components. These are like self-contained subnetworks.
Little islands.
Exactly. All nodes inside one component can reach each other, but they can't reach nodes in a different component.
And there's usually a big one.
Often, yes. The largest is called the giant component, especially if it contains a really substantial chunk, often the vast majority of all the nodes.
I can see why that's important. I mean, talking about average path length doesn't mean much if you can't even get from A to B.
Precisely. It only really makes sense within a connected component, usually the giant one.
And it gets trickier with directed links, right? Like Twitter retweets where info flows one way.
It does add complexity. We talk about weakly connected components if we just ignore the directionality.
Treat them like 2-way streets for a moment.
Yeah, basically. But then there are strongly connected components that's much stricter.
Oh, so.
For a set of nodes to be strongly connected, there has to be a directed path between every pair of nodes in both directions.
So if I can retweet you, you have to be able to retweet me, maybe through others. But the path has to exist both ways.
That's it exactly. Think of it like a real conversation, information flowing back and forth freely.
Gotcha.
In networks with lots of one-way follows, you'll have many weakly connected components, but probably far fewer strongly connected ones.
And the size and number of these components matter.
Hugely. For network resilience, how fast information spreads, how easily the system might fragment. I mean, the internet relies on maintaining that giant component for global reach.
Right. Okay, now, this next concept is probably one of the most famous, maybe mind-bending ideas, the small world effect.
Ah, yes. 6 degrees.
6 degrees of separation. You, the listener, ever wonder how many steps you are from, I don't know, an Olympic athlete, your favorite actor? Or, as our source material asks in Korean, how many degrees are you from Chimchakman, the webtoon artist Lee Malnyeon?
It's fascinating. And the idea really gained traction with Stanley Milgram's classic experiment in the 60s.
The letter forwarding one?
That's the one. People in the Midwest trying to get letters to Boston just through personal acquaintances.
Did it work?
Well, not all letters made it, only about 26% actually. But the ones that did arrive took, on average, about 6 steps.
6 steps, that's where it comes from.
That's the empirical basis for the 6 degrees idea, suggesting that even in huge social systems, the average path between any two people is surprisingly short.
And it's not just academic, it's everywhere in pop culture.
Totally.
The 6 degrees of Kevin Bacon game.
Linking actors through movies.
Or the Urdu's number for mathematicians, linking them back to Paul Urdu's through collaborations.
Right. They're fun, but they illustrate this profound network property. The world feels small.
So what makes it small? What's the science?
Well, the really significant work here was by Duncan Watts and Stephen Strogatz. They built a model.
Right.
And they showed that these small world networks have 2 key features. One, they're highly clustered.
Meaning friends of friends are often friends, like local communities?
Exactly. Very clustered, like a regular, predictable grid. But, and this is the kicker, they also have very small average path lengths, similar to a completely random network.
How can they be both structured and random like short?
The magic ingredient is shortcuts. You only need to add a few random long-range links into that highly clustered local structure.
Just a few random connections.
Just a few. Those shortcuts act like highways across the network.
So it's this amazing balance then, strong local neighborhoods, but with a few expressways connecting everything.
That's a perfect way to put it. Those few shortcuts drastically slash the average distance between any 2 nodes across the whole network.
Without wrecking the local communities.
Exactly. In a purely regular grid, path length grows linearly with size, gets bigger, proportionally. But in these small world networks, thanks to the shortcuts, path length grows incredibly slowly, often logarithmically.
Which is why huge networks still feel small.
That's the essence of the small world phenomenon.
Okay, so if those shortcuts make the world small, let's go back to the clustering that gets preserved. You said it's basically asking, are friends of my friend also my friend?
That's the core idea. For any specific node, let's say, its local clustering coefficient measures exactly that. What fraction of pairs of your friends also know each other?
So if all my friends know each other, it's high. If none do, it's 0.
Correct. And then transitivity is the network-wide version. It looks at all possible triangles, 3 nodes all connected to each other, and asks what fraction of those potential triangles actually exist in the network.
And why does this clustering matter so much?
Because we see it everywhere. Real social networks, biological networks, even some tech networks have significantly higher clustering than you'd expect if connections were just random.
So it's not a fluke, it's fundamental.
It tells us that these tightly knit local groups, these communities, are a basic building block of connected systems. It implies cohesion, trust, shared context within those groups.
Makes sense. We see those cliques in communities all the time. How does it show up on, say, social media?
Well, take Twitter retweets. Often, a cascade looks like a star one source, many retweeters.
Right.
But you start seeing triangles form when people participate in multiple cascades from different sources within a similar topic.
Right.
That overlap builds clustering within communities focused on specific interests.
Ah, so my friends retweeting things and their friends retweeting, that interaction shapes the bigger structure.
Precisely. Those micro-interactions build the macro structure of information flow and community.
Okay, so we've got connections, paths, distances, components, this small world idea, clustering. What does it all mean for figuring out who or what is important in a network?
Right. This brings us to centrality measures.
Because not all nodes are created equal, right? We see this heterogeneity.
Definitely. A few nodes are often vastly more connected or influential than most others. It's often a power law distribution.
Right.
Think of major hub airports. Atlanta's Hartsfield-Jackson compared to a small regional airport, or Google.com versus a tiny personal blog.
Orders of magnitude difference.
Exactly. And identifying these hubs and measuring their centrality is crucial. They often dictate flow, resilience, vulnerability, influence.
And the simplest measure we already touched on, degree centrality, just counting connections.
The most basic, yes.
Right.
Who has the most friends? Which web page has the most incoming links? Simple, but often very informative.
But just a starting point, what else is there?
Well, there's closeness centrality, this asks. How close, on average, is a node to all other reachable nodes in the network?
So not just direct connections, but overall reach.
Exactly. A node with high closeness can get information out quickly to everyone, or information can reach it quickly. Think about emergency broadcast. You want high closeness.
Good point. Okay, and then there's one that sounds really interesting. Betweenness centrality. This one finds the bridges, the bottlenecks.
This one is fascinating for understanding control and flow. Betweenness centrality measures for a specific node or link what fraction of all the shortest paths between other pairs of nodes pass through it.
Whoa. Okay, unpack that.
So a node might not have that many direct connections, low degree, but if it's the only way, or on the shortest path, for two large groups to communicate,
It's critical.
its betweenness centrality will be sky high. Imagine that single bridge connecting two islands again. All traffic has to go over it. Removing it disconnects things or forces much longer routes.
So these high betweenness nodes are the gatekeepers, the essential connectors, even if they aren't the most popular.
Precisely. They often sit between distinct, tightly clustered communities. And actually, measuring betweenness is a common way to find those community boundaries. High betweenness links often bridge different communities.
Very clever. Okay, but if we're talking pure influence, especially online, we have to talk PageRank.
PageRank. Yes. The algorithm that basically built Google Search, developed by Sergey Brin and Larry Page.
And it's a type of eigenvector centrality. Sounds complicated.
The math can be, but the core idea is elegant. It's recursive. A page's importance, its PageRank, isn't just about how many links point to it.
Okay.
It's crucially about the importance of the pages doing the linking. A link from a highly important page is like a stronger vote of confidence.
So getting a link from a major news site is worth more than a link from my tiny blog.
Infinitely more. In practice. Marissa Mayer, back when she was at Google, famously said something like, "Math professors love us because Google made eigenvectors relevant to every matrix algebra student."
I bet it really showed the power of that math.
It really did.
And the algorithm has that teleportation factor, around 0.15. What's that doing?
That's a clever bit. It simulates a web surfer randomly jumping to any page on the web instead of always following links.
Why do that?
Two main reasons. It ensures the math always works out, it converges to a stable answer, and it prevents rank sinks pages that accumulate importance but don't link out, trapping the flow. It ensures even isolated pages have some tiny chance of being found.
Makes sense. And the sources mention the constant fight against spam dexing, like link farms.
Oh, yeah. People trying to artificially inflate PageRank by creating networks of pages that just link to each other. It highlights how critical these algorithms are, but also how they're constantly being gamed. It's an ongoing battle in managing online information.
Wow. Okay, so there you have it. A real deep dive into these invisible but incredibly powerful network structures. From, birds of a feather, assortativity, all the way to 6 degrees of separation and the crucial roles of these central hubs and bridges. We've covered a lot of ground.
We have. And I think the key takeaway is that these concepts aren't just abstract theories.
Right.
They push us to think more critically about how information actually flows, how communities form, maybe how vulnerable we are to those echo chambers we talked about.
That dark side of homophily.
Exactly. Understanding this stuff is the first step towards navigating it better. Knowledge is most valuable when you can actually apply it, when you see it in the world around you.
So a final thought for you, the listener. Next time you connect with someone new online or retweet something or even just browse the web, take a second. Consider the unseen network dynamics. How do your connections play into that small world effect? What role do you play, maybe unknowingly, in how information moves through these incredibly complex interconnected systems? Something to ponder. Welcome to the Deep Dive, your shortcut to being truly well-informed. Today we're diving into the invisible threads connecting everything around us. Think the internet, your social circle. We're talking about networks, these hidden structures that are, well, everywhere. And it really makes you wonder, doesn't it? Like, what if the way things are linked together actually changes everything? How resilient they are, how information zips around, maybe even how they break.
That's exactly the core question. And our mission today is to unpack that, focusing on complex networks, and specifically this idea of scale-free networks.
Scale-free, okay.
Yeah, we'll look at how you define them, what makes them different, this recent big debate about whether they're actually everywhere, and crucially, why understanding this architecture is just so vital today. We've got sources from like academic talks, cutting-edge papers, even art, which is pretty cool.
Art, interesting. Okay, let's unpack this. So networks. We mean nodes, right? Entities, people, computers, whatever. And links, the connections.
Exactly, nodes and links.
But how do you even find them? You said they're invisible. The internet doesn't exactly hand out a map. So how do we actually see these structures in the real world?
That's a great point.
Yeah.
You need methods sort of like detective work for networks. One way is node sampling. You just pick some nodes, say a few specific websites, and then you trace all their links.
Okay.
Or you can do link sampling, focus on the connections themselves, like maybe tracking email exchanges, and then see which nodes pop up at either end. And then there's snowball sampling, which is probably the most intuitive one. You start with one node, like one person.
Right.
Ask who their friends are. Then you go to those friends and ask who their friends are. You just expand outwards, layer by layer, like a snowball rolling downhill, getting bigger.
Got it. That makes sense. So clicking a link on the web, I'm basically walking along one path in this giant network. Who's doing that sampling, that mapping for the whole web? It must be automated, right?
Oh, absolutely. It's not people doing it manually. That would be impossible. We use automated programs. You've probably heard of them, web crawlers or spiders.
Spiders, yeah.
They start with a list of known web addresses, the seeds, and then they just go. They follow every hyperlink on every page they visit, add those new links to their list, and just keep crawling, indexing, mapping. It's this constant, tireless process. Search engines, like Google, depend entirely on these crawlers to keep their picture of the web up to date. They're the digital map makers.
Okay, so these crawlers build the map. And you mentioned art. It's wild that these same underlying connection patterns are inspiring artists, not just scientists.
Yeah, absolutely. There's an artist, Tomas Saraceno. He actually trained as an architect, which is interesting. But his work is deeply inspired by networks. He looks at spider webs, neural networks.
Yeah.
Pulls ideas from engineering, physics, biology, and translates these complex, often abstract network structures into these really stunning physical installations. You might see his stuff in major museums, like in Miami. It's quite something.
Wow. Okay, so we can find these networks, even get artistic about them. But let's get back to the structure. You said the way they're connected matters. How different can these connection patterns actually be?
That's the crucial point. The differences can be profound. And the key concept we use to measure this is called the degree distribution.
Degree distribution.
Yeah, it's basically just a way of asking. If you pick a node, totally at random, what's the probability it has, say, 5 links or 10 links or 100 links? It charts the popularity, if you like.
Okay.
So let's contrast the two main characters here. First, you have random networks. Think of the early models by Erdős and Rényi. In these, most nodes have roughly the same number of connections, clustered around an average.
Like a bell curve.
Exactly like a bell curve, or more technically, a Poisson distribution. Very few nodes have tons of links. Very few have almost none. Most are just average. There aren't really any massive standout hubs. Think of a city grid where most intersections have, 4 roads meeting. Pretty uniform. But then you have scale-free networks. And these are completely different. They're highly uneven, or inhomogeneous is the technical term.
Okay.
You have loads and loads of nodes with very few links, your tiny cul-de-sacs maybe. But then you have a few nodes, the hubs, that have an absolutely huge number of connections.
The big airports.
Precisely. The airline network is the classic analogy. Lots of small regional airports, maybe 1 or 2 flights a day. Then you've got Chicago O'Hare, Atlanta, Dubai, massive hubs connected to almost everywhere. That hub structure is the defining feature.
That analogy really helps. So if I'm looking at data, how do I actually spot one of these scale-free networks? What's the visual giveaway?
Good question. The trick is how you plot the degree distribution. If you plot it on what's called a log-log plot.
Log-log, both axes logarithm.
Both axes, yeah. If the network is scale-free, its degree distribution will look like a straight line going downwards on this log-log plot. That straight line is the signature of a power law.
A power law, okay.
Yeah. And the steepness of that line, the slope, tells you something important about how dominant those hubs are. A random network, plotted the same way, looks totally different. It curves downwards much faster, especially out in the tail, where the really highly connected nodes would be.
Got it. So that straight line is the key.
It's a big clue. For instance, back in '98, researchers looked at the World Wide Web. They plotted the distribution of incoming links to web pages and outgoing links from web pages.
I bet.
Both showed up as straight lines on a log-log plot. Bang! That told them the web wasn't just some random mess of pages. It had hubs, these incredibly highly linked sites. That was a huge discovery.
So scale-free.
Yeah.
It's not just a catchy name then. It means something fundamental about the network structure. No typical scale.
Exactly. Scale-free means there's no characteristic number of links. It's not like you can say, oh, the average node has about 10 links, and most nodes are close to that. No.
Yeah.
The number of links stretches across vastly different scales, many orders of magnitude. In a finite network, the biggest hub just keeps getting bigger relative to the average as the network grows. The difference between the node with the fewest links and the node with the most links can be, tens, hundreds, even thousands of times larger than a random network of the same size. It's that extreme inequality.
We hear a lot about the small world idea, 6 degrees of separation, how we're all surprisingly close. Do scale-free networks affect that?
They take it to a whole new level. So yeah, the basic small world property means the average path between any two nodes is short, typically growing logarithmically with the network size, like log n.
Right.
But scale-free networks, because those hubs acting like superconnectors, often exhibit what's called the ultra-small world property.
Ultra-small. Even smaller.
Even smaller distances, yeah. Instead of scaling with log n, the average path length in many scale-free networks scales with, wait for it, log n. Logarithm of the logarithm. Yep. Sounds abstract, but the effect is dramatic. Let's take your social network example. Say 7 billion people. In a standard random-ish small world, log n might give you an average path length around, 22 or 23 steps.
Okay. 6 degrees is looking pretty good there.
Right. But in a scale-free network with the same number of people, log n might be just 3 or 4 steps.
3 or 4? That's tiny.
Radically shrinks the world. Everything becomes incredibly close because you can just hop onto a hub and get almost anywhere else super quickly.
Okay, that's astonishing.
True.
If the hubs are that powerful, shrinking distances so much, what does that imply for how the network actually works? Its dynamics, its weak points?
It means the hubs basically run the show. They dominate everything. Information flow, disease spread, it all gets channeled through these hubs. And in some, theoretical extreme scale-free networks, the average path length barely even increases as the network grows. It's like the whole thing acts as one giant, tightly connected unit, which sounds great, but
there's a catch.
There's always a catch.
So for a long time, it felt like scale-free was the answer, found in biology, tech, social systems, like this universal blueprint. But then recently, people started questioning that. What happened?
Yeah, exactly. After that initial burst of excitement around 99, 2000, finding power laws everywhere became, almost fashionable. Scale-free seemed universal.
Right.
But then came this paper in 2019, Scale-Free Networks Are Rare, by Anna Broido and Aaron Closet. And it definitely made waves. They took nearly 1,000 real-world network datasets, social, biological tech, the works, and applied much more rigorous statistical tests.
More rigorous how? What did they do differently than just looking for that straight line on the log plot?
But their big emphasis was on statistical goodness of fit. They argued quite convincingly that just eyeballing plots is risky. The eye loves finding straight lines.
Guilty as charged.
Yeah, we all do it. So they use sophisticated tests, like the Kolmogorov-Smirnov test, to mathematically quantify how likely it was that the observed data actually came from a true power law distribution versus some other distribution. They were really careful about identifying where the power law behavior might even start this common value.
Okay.
They also stressed using better plotting techniques like log binning or looking at the cumulative distribution, which give you a clearer view of the tail, that crucial high-degree end, rather than letting noise obscure it.
And their conclusion?
Nah.
After all that rigor?
It was pretty stark. They found that only about 4% of the nearly 1,000 networks they looked at could be classified as strongly scale-free, according to their strict criteria.
Only 4%?
Yeah. For most networks, other mathematical distributions, like the log-normal distribution, actually fit the data just as well, or sometimes even better. And they specifically noted that social networks often looked, at best, weakly scale-free. Not quite the hub-dominated picture we had.
Wow, okay. That is a shakeup. How did the network science world react? People must have had strong opinions.
Oh, huge reaction. Massive online discussions, blog posts.
Yeah.
It really kicked off a debate. Albert Laszlo Barabasi, who was one of the pioneers of scale-free networks, wrote a pretty pointed response.
I bet.
His main argument was kind of technical but important. He said Broido and Closet were making a conceptual error by applying statistical tests designed for finite data sets to a concept, true scale-freeness, that's mathematically defined only in the limit of an infinitely large network.
Ah, the infinite versus finite problem.
Exactly. Real networks are always finite. Barabasi argued that natural fluctuations in a finite network, even one that's growing towards being scale-free, might cause it to fail a strict statistical test. He also raised some specific technical points about their methods.
So a clash of interpretations.
Definitely. Others tried to bridge the gap. Peter Holmes suggested maybe it's partly about terminology and that maybe the reality is somewhere in between rare and everywhere. He also made the really important point that we need better theories specifically for finite networks because that's what we actually deal with. We can't just apply infinite limit math and expect a perfect match.
That seems sensible.
Yeah, and there are other complexities too, like networks that might follow a power law for a bit and cut off exponentially, or even mathematical rules saying you literally can't build a network if the power law is too extreme, the graphicality problem. So the picture is, well, it's complex.
It always is. Okay, stepping back from the purely academic debate, why does this actually matter? Why should we care if a network is truly scale-free or log-normal or something else? What are the real-world stakes?
It matters immensely because of those fat tails or heavy tails we talked about with power laws.
Fat tails, meaning extreme events are more likely.
Much more likely than in a normal bell curve world. Think about it. Earthquakes, market crashes, maybe even the success of blockbuster movies. Many phenomena seem to follow these power laws, where extreme outcomes aren't just possible, they're almost expected eventually.
Right. The unexpected happens more often.
Exactly. And it connects directly to something like the Pareto principle, the 80-20 rule. 80% of the wealth held by 20% of the people, or 80% of software bugs caused by 20% of the code.
Yeah.
That 80-20 pattern is often a signature of an underlying power law distribution. It shows how a small number of things, the hubs, the vital few, can have a vastly disproportionate impact. Understanding the distribution tells you whether to expect that kind of concentration of influence or resources.
Okay, so it affects extremes in concentration. What about resilience? You mentioned a catch earlier. How does the network structure affect its ability to handle, say, failures or attacks?
This is maybe one of the most critical practical insights. Network robustness. How does it hold up when nodes get knocked out?
Right.
Let's take the contrast again. Your standard random network, surprisingly fragile against random failures. If you just start randomly deleting nodes, you only need to remove a certain fraction at a critical threshold, and the whole thing can suddenly shatter into disconnected pieces.
Okay.
However, random networks are less bothered by targeted attacks. If you try to deliberately take out the most connected nodes, well, there aren't really super connected nodes, so the damage is more limited.
Makes sense. No big targets.
Exactly. Now, scale-free networks. This was the huge finding by Albert Jiang and Barabasi back in 2000. They are incredibly robust against random failures.
Robust? How so?
Because most nodes have only a few links. If you randomly delete nodes, you're overwhelmingly likely to hit one of these unimportant low-degree nodes. Removing them barely makes a dent in the overall connectivity. You can delete a huge percentage randomly, and the network often just shrugs it off, staying connected via the hubs.
Wow. Okay, so they tolerate errors really well.
Right.
Right.
That error tolerance comes at a massive cost. Scale-free networks are extremely vulnerable to targeted attacks.
Ah, the Achilles heel.
Precisely. If you identify and remove just a few of those critical high-degree hubs, the whole network can collapse catastrophically. You take out the main airports, and the entire airline system grinds to a halt.
Right. That makes intuitive sense now.
And this isn't just theory. Early studies on the actual internet infrastructure, at the level of routers and on the World Wide Web, showed exactly this pattern. Highly tolerant to random nodes going offline, which happens all the time, but potentially crippled if key hubs were attacked. understanding that vulnerability is vital for security, for designing resilient systems. And it's fascinating. Some researchers like S.A. Frank argue these patterns might even emerge naturally from really simple processes, like systems just trying to preserve certain kinds of information efficiently. It's almost like nature stumbles upon this structure sometimes.
What a journey. So we've gone from just nodes and links to mapping the invisible web to these dueling structures, random versus scale-free, and the immense power of hubs, and then this whole fascinating debate about whether scale-free is really universal, and finally landing on these critical real-world consequences for robustness and vulnerability.
Yeah, it covers a lot of ground. And I think the key takeaway, whether these pure scale-free networks are ultimately judged rare or common, is the importance of understanding the power law distribution itself. Those heavy tails, the Pareto principle, they show up in so many places. Grasping their implications is just essential for making sense of extreme events, inequality, and for building things that last.
Absolutely. This deep dive really highlights how this unseen architecture, the way things are connected, profoundly shapes, well, almost everything: communication, biology, society. Seeing these patterns helps us understand, predict, maybe even design better. So here's something to think about as you go about your day. Look at a system in your life. Could be your work colleagues, your friends on social media, maybe how news or gossip spreads. Does it feel pretty uniform, sort of random? Or can you spot potential hubs, those super connectors? And if you do see signs of that scale-free dynamic, that hub structure, what might that mean for how robust that system is? Or where its hidden vulnerabilities might lie? Something to chew on.
Welcome to the Deep Dive. We're the place you come to get the key insights on complex topics, all sort of broken down for you. Today, we're plunging into the really fascinating world of network models.
Yeah, network models.
Our mission, really, is to explore these ingenious, well, recipes, I guess, that scientists use to build artificial networks, the kind that mimic the real ones you interact with every single day. It's all about understanding those hidden rules, the ones governing the complex webs of connections that are literally all around us.
And what's truly essential here, I think, is how these models help us get a handle on the fundamental properties of networks.
Like how things spread.
Exactly. Yeah. How easily information spreads, or maybe why some connections just become way more central than others.
Okay.
We've pulled together quite a stack of material for this, foundational papers, some really recent insights too, from places like Gyeongsang National University. It's going to be interesting.
Yeah, definitely. And when you think about it, like your own social circle or the internet, even biological systems, they all seem to share these surprising traits, don't they?
They really do. It's remarkable.
First, you've got these incredibly short paths between almost any 2 points.
Right, the whole 6 degrees of separation thing.
Yeah, and then there's lows of triangles, where your friends are also friends with each other. High clustering.
High clustering. Very typical of social networks.
And finally, you see some nodes, some connection points that are just vastly more connected than others. We call those hubs. Right?
That's them, the hubs. And the really profound part, I find, is watching how these seemingly simple properties just emerge.
From complex interactions.
Exactly, from all these individual connections adding up. And network models, they're basically our tools to try and reverse engineer how that happens, to figure out where these properties actually come from.
It's like trying to understand how a city grows, maybe, without a map or any urban planning principles.
That's a good analogy, yeah.
Networks are kind of similar. Before we can really get how they work, we need some kind of blueprint, a model.
A starting point.
So let's nail down these universal traits again. We see them in countless real networks. 3 big ones stand out. First, those short paths. It takes, surprisingly few steps or hops to get from any node to almost any other.
That's the idea. It's often logarithmic with the size of the network, which is incredibly short.
And that 6 degrees of separation idea, it's not just like a fun fact. It's a real thing in many networks. Shows how connected everything is.
It really does. Small world phenomena.
Okay, second, high clustering. Nodes tend to clump together, right? They form these dense interconnected groups. So if A is connected to B and B is connected to C, there's a pretty high chance A is also connected to C. Forms that triangle.
Exactly. It's why your friends often know each other. It's not just coincidence. It's built into the structure.
And third, maybe the most striking one, heterogeneous degrees, or, the hubs.
The hubs, yeah. Connections just aren't spread out evenly at all.
Some nodes are incredibly well connected, like a major airport hub, maybe.
Perfect example. While most nodes, like most local airports, only have a few connections.
Right. So this brings up the big question.
How does this all happen? How do these universal properties actually come about? How do individual nodes pick their neighbors? What specific mechanisms create those really critical hubs?
Yeah.
Network models are basically our simplified descriptions. Often they're mathematical, sure, but they try to capture intuitions or specific hypotheses about how these features emerge.
So you follow the model's recipe.
Right. You build a network according to its rules, and then you compare that artificial network to real-world examples. That comparison tells you if your recipe, your hypothesized mechanism, actually holds water.
Okay, let's start simple then. What if we assume connections are just completely random? Is that a model?
It is. That's the core idea behind the Erdős-Rényi random graph, often called the ER model.
ER model.
Okay. It's sort of the simplest baseline, an egalitarian approach, you could say, or maximum entropy. Basically, you assume you know nothing except maybe the number of nodes and the average number of links.
So how do you build it?
Imagine you have your nodes. For every single possible pair of nodes, you just flip a coin. Heads, they connect. Tails, they don't. With some fixed probability p.
Just pure chance for every possible link.
Pure chance. And what's amazing is that even with just that randomness, something really critical appears. It's called the giant component.
Giant component.
Yeah. As you gradually increase that linking probability p, or just the average number of connections per node, right around an average degree of 1, suddenly, boom.
What happens?
A huge interconnected cluster just sort of percolates through the network. It connects up a really significant fraction of all the nodes all at once.
Wow. So even randomness creates some large-scale structure.
It does eventually. But, and this is a big but.
Uh-oh, here it comes.
When you compare this ER model to real networks, it runs into serious problems pretty fast.
Like what?
Well, remember the hubs. The ER model predicts that most nodes will have roughly the same number of connections. You get this very symmetrical bell-shaped distribution. Technically, it's a Poisson distribution. Think of a small town where everyone knows roughly the same number of people. No big social butterflies, no real hermits.
But real networks aren't like that. They have those hubs.
Exactly. That's a profound problem for the ER model. Our sources, they state it very clearly. The random network model does not provide a good description. The nodes have approximately the same degree, so there are no hubs.
So its main value is showing us what doesn't work.
In a way, yes. Its failure is incredibly informative. It tells us immediately that real network formation isn't just random chance. There are specific mechanisms at play.
And what about clustering, those triangles?
Very low in ER models. Those triangles are rare. It does give you short paths, surprisingly, which is one aspect of the small world property, but it fails on hubs and clustering.
Okay, so random isn't enough. We need a model that gives us both the short paths and the high clustering we see in real life.
Precisely. And that challenge led Duncan Watts and Stephen Strogatz to develop their famous small world model, the WS model.
The WS model. How does that one work? What's the mechanism?
It's quite clever, actually. It starts not with randomness, but with extreme order. Imagine a ring lattice, like nodes in a circle, where each node is only connected to its immediate neighbors, say it's 2 neighbors on each side.
Okay, so very regular, very clustered. Everyone's friends know each other in that little local group.
Exactly. High clustering baked in. But the paths are long, right? To get to someone on the opposite side of the ring takes many steps.
Right. So what do?
Then they introduce just a tiny bit of randomness. With a small rewiring probability, they could come and you pick an edge, disconnect one end, and reconnect that end to a completely random node somewhere else in the network.
Just randomly rewire a few connections.
Just a few, and the effect is dramatic.
What happens?
You see an almost immediate sharp drop in the average shortest path length. The network becomes small very quickly.
Because of those random shortcuts spanning the ring.
Exactly. But crucially, because you only rewired a few links, the overall clustering coefficient remains high, almost as high as the original ordered lattice.
Ah, so you get both short paths and high clustering.
That's the insight. It's this elegant way to bridge the gap between perfect order and total randomness. Our sources really highlight this, saying the model is capable of generating with a suitable amount of randomness networks endowed with 2 desired features: short paths and high clustering.
And I think we also saw something about a Newman-Watts model. Is that related?
Yeah, it's a slight variation. Instead of rewiring existing edges, it achieves a similar small world effect by simply adding new random shortcut edges to the original lattice.
So add links instead of moving them.
Yeah.
Similar outcome.
Similar outcome, yes. And interestingly, our sources even point out some fascinating mathematical equivalences. Under certain conditions, the Newman-Watts model is actually equivalent to another model called the Harari model. Yeah, it just shows how deeply connected these ideas can be, even when they come from slightly different starting points or fields. The details of how you build the model matter.
Okay, so Watts-Strogatz and Newman-Watts, they solve the short path and high clustering problem. That's a big step.
It is.
But
yeah.
I'm guessing there's still a catch. What about the hubs?
You got it. Still no hubs. The degree distribution in the WS model, as you increase that rewiring, it just shifts from everyone having the exact same degree in the perfect lattice to more of a bell-shaped curve again.
Like the random graph.
A bit like it, yeah. Certainly not the highly skewed distribution with massive hubs that we see in real networks. It never accumulates those really disproportionately large numbers of links on a few nodes.
So WS gets us closer, but it's still not capturing that really uneven connectivity. It doesn't explain the superconnectors.
Precisely. We're still missing the mechanism for the hubs.
Okay, so the hunt for the holies continues. How do we get networks with those true hubs, that wildly varying degree of connection that's so obvious in the real world?
Well, one tool people use to think about this is something called the configuration model.
The configuration model. Okay, what's the idea there?
It's less about explaining how a network structure arises and more about exploring the consequences of a given structure. It lets you build a network where the nodes have exactly the number of connections you specify beforehand.
You predefine the degree for every single node.
Exactly. You specify the entire degree sequence. Say, node 1 has 5 connections, node 2 has 2, node 3 has 50, whatever you want.
How does it build the network then?
It's quite neat, conceptually. Imagine each node has a number of little stubs or half-links sticking out of it, equal to its desired degree.
Okay, like little connection points waiting to be joined.
Right. Then you just randomly pick pairs of these stubs from anywhere in the network and connect them, forming a link. You keep doing that until all the stubs are paired up.
Ah, I see. So if I wanted hubs, I could just tell the model to give a few nodes a huge number of stubs, and most nodes only a few, like inputting a power law distribution.
Precisely. You could feed it a power law degree sequence, and it would construct a network that has that exact distribution, complete with hubs.
So it can make hubs.
It can generate a network with hubs, yes. Its main purpose is to let us study the pure effects of having a specific degree distribution, isolating it from other factors.
There's always a but.
But here's the critical takeaway, and our sources emphasize this. While it can generate a network with, say, a power law distribution, it offers absolutely no mechanistic explanation for how that distribution came about in the first place. It doesn't tell you why the network grew that way.
It just builds to spec, basically. Doesn't explain the origin story.
Exactly. And maybe even more importantly, even when you give the configuration model a power law degree sequence, the kind that should have hubs, it generally produces networks with much lower clustering coefficients than we see in real social networks.
Really? Even with the right degree distribution?
Yep. Our sources point this out quite clearly. The degree sequence or distribution cannot explain the clustering coefficient.
Wow. Okay, so just having the right number of connections per node isn't enough to get the local structure, the triangles, right.
It's not sufficient. It tells us something else is going on.
So what this all means then is we need more than just a model that can reproduce a structure. We need one that actually explains the origin of that structure.
We need a plausible, mechanistic explanation, as the researchers say. A story of how the network grew to look the way it does.
And that quest for a mechanism, that brings us somewhere important, doesn't it?
It brings us to a really pivotal breakthrough in network science, the Barabasi-Albert model, usually called the BA model.
The BA model. Okay, this sounds significant.
It really was, because it offered a powerful and actually quite simple mechanistic explanation for how hubs and those power law degree distributions naturally emerge.
What's the mechanism? What are the key ingredients?
There are really just two simple intuitive ideas. First, growth. Networks aren't static. They expand over time as new nodes join. Think of the web adding new pages or new people joining a social platform.
Okay, growth makes sense. What's the second ingredient?
Preferential attachment. This is the crucial part. When a new node joins the network, it doesn't just connect randomly. It's more likely to connect to nodes that already have many connections.
Ah, so the popular nodes get more connections.
Exactly. It's often called the rich get richer phenomenon or the Matthew effect. Popular websites get linked to more often, making them even more popular. Well-connected people tend to make new connections more easily.
That sounds plausible, almost obvious in retrospect.
It does, doesn't it? And what's truly compelling is that this elegantly simple pair of rules growth and preferential attachment naturally, almost inevitably, leads to networks with a specific structure.
Which is?
A scale-free power law degree distribution.
Scale-free? What does that mean exactly?
Scale-free means the network looks statistically similar regardless of the scale you're looking at. Whether you zoom way in on a small part or zoom way out, you still see that same relative pattern. A few massive hubs dominating, and lots of nodes with very few connections. There's no typical scale or size for a node's connectivity.
Unlike the bell curve from the random or WS models, which has a very clear typical scale.
Precisely. This scale-free structure, generated by the BA model, matches the patterns observed in an incredibly diverse range of real-world systems. The World Wide Web, citation networks, social networks, protein interaction networks.
Oh, wow.
Yeah. As our sources note, the development of large networks is governed by robust, self-organizing phenomena that go beyond the particulars of the individual systems. Preferential attachment seems to be one of those robust phenomena.
And you can test this, right? Like, what if you change the rules? What if new nodes don't attach preferentially?
Great question. If you have growth, but new nodes just attach randomly, or maybe even preferentially to less connected nodes, those dominant hubs simply disappear. You lose the power law distribution.
So that preferential attachment rule is absolutely key for creating the hubs.
It really seems to be the driving force behind that feature. There are variations like nonlinear preferential attachment, where the preference is stronger or weaker, and that affects the exact shape of the distribution, but the core idea holds.
Okay, so the BA model is huge. It explains the hubs and the scale-free nature using a simple, plausible mechanism, growth and preferential attachment.
Yes, a major step forward.
But it does get everything right. What about the clustering, the triangles?
There's the rub. While the BA model brilliantly explains hubs and scale-free properties, the basic version often still falls short on the third key property, high clustering.
Still?
Yeah. The networks it generates tend to have lower clustering than many real-world networks, especially social networks, which often exhibit both prominent hubs and a high density of triangles.
Okay, so we're getting closer, but maybe still missing a piece for some networks.
Seems like it. We need a way to get hubs and triangles together naturally.
Before we get to that final piece, though, this idea of hubs and how connections aren't random, it actually explains something kind of personal, doesn't it? Something called the friendship paradox.
Yes. The friendship paradox. It's a fantastic, counterintuitive result that connects directly to network structure.
Have you ever had that feeling, maybe scrolling through social media, that on average, your friends seem to have more friends than you do?
It feels like that sometimes, right?
Yeah.
A bit deflating, maybe.
Yeah. But the paradox is, it's actually mathematically true, isn't it?
It is generally true, on average. Our sources absolutely confirm this. It's not just a feeling or some kind of personal insecurity. Statistically, your friends do tend to have more friends than you do.
Okay, wait. How does that work? Let's unpack that.
The explanation lies in something called biased sampling. Think about how you encounter your friends. You are, by definition, more likely to be friends with someone who has many friends, simply because they have more connections through which you could have met them. Those highly connected people, the hubs of the social network, show up in many people's friend lists.
So I'm more likely to sample the popular people when I'm counting my friends.
Exactly. They are overrepresented in the collection of people who are your friends. Your friendship circle isn't a random sample of the population. It's biased towards those who are more connected.
Because the hubs, by definition, have more links pointing to them, making them more likely to be on my list.
Precisely. It's a direct consequence of that uneven, scale-free distribution of connections that models like BA help us understand.
Wow. That's mind-bending, but makes sense.
It really highlights the impact of network structure on even our perception of our social world. And understanding the sampling bias is actually critical in other fields, too.
Like what?
Think about epidemiology. If you want to find potential superspreaders during an epidemic, asking people to name their friends might be a surprisingly effective way to find individuals who are more connected, and thus potentially more central to spreading than average.
Because their friends are likely more connected than they are.
Exactly. Our sources even quote network scientist Mark Newman on this. He says, basically, your friends just are not normal. No one's friends are. By the very fact of being someone's friend, friends select themselves. Your circle of friends will be a biased sample of the population because of it.
Fascinating. Okay, so let's loop back. The BA model gives us hubs via preferential attachment, but maybe not enough clustering. Wastrogas gives high clustering and short paths, but no hubs.
Right. We need to put it all together.
So how do we get a model that successfully captures all three key features? Short paths, high clustering, and the hubs, the scale-free distribution.
That's where newer, slightly more complex models come into play. A good example is the HomeKim model.
HomeKim. Okay, what's their approach?
They essentially take the Borabasi-Albert model as a foundation. They keep the core ideas of growth and preferential attachment, which generates the hubs and the scale-free property.
Okay, so they start with BA.
But then they add one extra step specifically designed to boost clustering. It's an explicit mechanism for triadic closure. Remember the triangles?
Yeah, A knows B, B knows C, so A gets connected to C.
Exactly. So in the HomeKim model, here's what happens. A new node joins. Step 1, it connects preferentially to an existing node. Let's call it node M. Just like in the BA model, rich get richer.
Okay, standard BA so far.
Step 2. Then, with a certain probability, the new node also connects to one of node M's existing neighbors.
Ah, so it deliberately closes the triangle. New node connects to M and also to one of M's friends.
Precisely. It builds in that triangle formation step right after the preferential attachment step.
That's clever. So you keep the hub generating mechanism.
Yes, you still get the power law distribution because of the initial preferential attachment.
And you simultaneously build in the high clustering that was missing.
Exactly. It allows you to generate networks that have both a scale-free degree distribution and a high clustering coefficient. And you can even tune how high that clustering is by adjusting the probability of that second triadic closure step.
And the path length. Still short.
Yes. The characteristic path length typically remains short, growing logarithmically with network size, just like in BA and WS models. It preserves the small world property, too.
So the HomeKim model, or others like it, kind of represent getting the full picture. Hubs, clustering, and short paths, all explained by a plausible growth mechanism.
It's definitely a significant step towards capturing those key empirical observations in a single generative model. It combines the insights from earlier models.
Okay, so today we've really taken a journey, haven't we? Through the evolution of these network models.
It really has.
Starting from, the simplest idea of just random connections with Erdős-Rényi.
And seeing its limitations, especially with hubs and clustering.
Right. Then moving to Wastrogas, which cleverly gave us short paths and high clustering, but still missed the hubs. Then tackling the hubs with the configuration model, realizing it could build them but not explain them, and still lacked clustering.
Leading us to Borabasi-Albert.
Yeah, the BA model with its elegant growth and preferential attachment, explaining the hubs and scale-free nature, but often falling short on clustering.
And finally arriving at models like HomeKim, which add mechanisms like triadic closure to BA, trying to capture all three properties, hubs, clustering, and short paths together.
It's quite a progression of ideas.
It really is. And understanding these different recipes for networks, these models, it really helps us grasp the underlying mechanisms driving so many different systems.
Social dynamics, how information or diseases spread.
Biological systems, protein interactions, technological infrastructure like the internet or power grids. It truly reveals the sort of invisible architecture of our incredibly interconnected world.
Yeah, so maybe next time you're scrolling through your social feed or just thinking about a new connection you made, maybe pause and think. What network properties do you see at play there?
Yeah, what stands out to you after hearing about all this? Do you notice the hubs, the clusters?
What did you take away from today's deep dive?
And maybe here's a final thought to leave you with. If even our closest social circles, our friendships, are subject to these really fascinating, sometimes counterintuitive mathematical biases like the friendship paradox, what other hidden structures, what other subtle network influences might be shaping our daily interactions, our opportunities, even our thoughts, without us even realizing it?
Something to definitely ponder as you navigate your own unique web of connections.
Welcome to the deep dive. Ever wonder how information spreads, or maybe why certain groups seem to stick together, whether that's online or, in real life? Today, we're cutting through some of the noise to understand the hidden architecture of the world around us. We're diving into communities and other mesoscale structures in network science.
Right. It's a fascinating area.
We've sifted through university lectures, some pretty cutting-edge research papers, and our own notes, of course. And our mission, as always, is to deliver the surprising facts and crucial insights you need to be truly well-informed.
It's really a journey into seeing the invisible forces that shape so much. Everything from how diseases might move through populations to maybe even how your own brain processes thought.
Okay.
We're looking for the patterns within the chaos, the natural groupings that tell us so much about how a system behaves.
Okay, let's unpack this then. When we talk about communities in networks, what exactly are we picturing? I mean, think of your own social circles, right? Or even how different parts of your brain light up together. We sort of instinctively see these groups.
Precisely. And network science gives us a formal way to talk about that.
Yeah.
Communities, sometimes called clusters or modules, are defined as sets of nodes, points in the network, that have a significantly higher density of connections within the group than they have between themselves and the rest of the network. Imagine like a busy neighborhood where most people know each other, interact a lot, but maybe only a few ever really connect much with people outside that immediate area. That's the core idea.
So why is finding these communities so important? What functions do they actually serve? Why is it such a big deal to study them?
Well, what's fascinating here is just how universal this concept is. It applies across so many different domains. Okay, so in the brain, for example, dense clusters of neurons, they often synchronize their firing patterns. And that directly indicates they're working together on some specific function, maybe processing something you see. Or in biology, you look at protein interaction networks. Groups of proteins that interact a lot often correspond to particular biological functions like metabolism.
Right.
On the internet, clusters of web pages linking heavily to each other usually points to a specific topic. And, crucially, in social networks.
Yeah, the social side is huge.
Absolutely. Communities of friends often share important features. Think political beliefs, for instance. And this can significantly influence public opinion. Our sources even highlighted how politically charged memes spread very differently depending on these online community structures.
Wow.
So if we want to understand how a rumor spreads or maybe halt an epidemic or even just ensure critical information gets out effectively, well, understanding these underlying community structures is absolutely key.
So if these communities are so crucial, how do we actually find them? I mean, sometimes for a tiny network, maybe you could just look at a diagram and see the clusters.
Maybe for a very small one.
But most networks we care about are way too big or complex for that. Simple visualization just won't cut it.
Exactly. And this is where the detective work really begins. The challenge of community detection. It's truly interdisciplinary. People call it community discovery clustering.
Lots of names for it.
Right. And it's considered an unsupervised classification task. That means, unlike some other problems, we don't always have clear examples beforehand of what the perfect division should look like.
Oh, okay.
There isn't even one single universally agreed upon definition of a community, though that core intuition, more links inside, fewer links outside, that's always there.
One of the early ways people tackled this was through something called network partitioning, wasn't it?
Yes, exactly. Network partitioning focuses on identifying these well-separated subnetworks. Often, the goal is specific. Divide a network into a given number of clusters, maybe even of given sizes.
Right.
While minimizing the cut size. That's the total number of links connecting the different subnetworks.
Okay, minimizing the connections between groups.
A classic example is graph bisection. You want to split a network into two equal-sized halves with the fewest possible connections running between them.
Makes sense.
The challenge, of course, is avoiding trivial solutions. Like, just cutting off a single node doesn't tell you much. Or having one huge cluster and one tiny one. That's usually not very informative.
Our sources mention a specific algorithm for this, the Kerneman-Lin algorithm. How did that work for graph bisection?
Right, Kerneman-Lin, or KL. It was a popular early method. It starts with just any old division, an arbitrary one.
Okay.
And then it iteratively swaps pairs of nodes between the clusters. The goal is to decrease that cut size with each swap. But crucially, it tries to maintain the balance, keep the clusters roughly the same size.
So it's trying to improve an initial guess.
Exactly. It's a bit like trying to find the best seating arrangement at a wedding with two rival families. You want to minimize the arguments across the aisle.
Ah, good analogy.
But as a greedy algorithm, it can get stuck. It might find a pretty good arrangement, but maybe not the absolute best one. It finds a local optimum, not necessarily the global one. So it's often used more as a refinement step these days.
Okay, so beyond just splitting into a fixed number of parts, there's this broader idea of data clustering based on similarity.
Yes, and that leads naturally into hierarchical clustering. This is a very popular technique. Imagine building a kind of family tree, but for network connections.
Our tree.
Yeah, a dendrogram. You can build it up or break it down. Either start with every node in its own tiny group and iteratively merge the most similar pairs. That's called agglomerative.
Bottom up.
Right. Or you start with the whole network as one big group and keep splitting it that's divisive, top down.
Okay.
The result is this tree structure. And then you basically decide where to cut the tree horizontally to get your final set of communities.
But how do you measure that similarity? That seems critical for deciding which groups to merge or where to split.
It absolutely is. You could use properties of the nodes themselves sometimes, but for network structure, structural equivalence is really key.
Structural equivalence.
Yeah, it measures similarity based on shared neighbors. Think about two people in a social network. They might not know each other directly, but if they have a lot of the same friends, they are structurally similar. Maybe they share 40% of their combined friends list. That gives you a similarity score.
I see, based on who they connect to.
Exactly. And when you're merging groups in hierarchical clustering, you need rules too. Like single linkage uses the similarity of the most similar pair between two groups. Complete linkage uses the least similar pair. Average linkage uses the average.
Okay, different ways to define group similarity.
But the catch with hierarchical clustering is often deciding where to make that cut in the dendrogram. There isn't always a clear, objective reason for one cut level being best. And, like KL, these methods can get quite slow for really large networks.
Right. This is where it starts getting really interesting, I think. These early methods were a start, but they hit limits with real-world complexity, didn't they?
They did.
So the next big step seems to have been finding a better way to measure if the communities we found were actually, good, meaningful.
Exactly. It wasn't enough just to divide things up. We needed an objective function, a score, to tell us if a particular division made sense structurally.
And that led to?
That quest led us to modularity, usually written as Q. It's arguably the most intensively studied concept for these mesoscale structures.
Modularity, Q. Okay. What does it measure?
Modularity basically asks this question. Are the connections inside the communities you've identified far more numerous than you'd expect if links were just placed randomly across the network, given the node's degrees?
Content or random chance.
Precisely. A high Q score means, yes, these communities are genuinely cohesive. They have significantly more internal wiring than a random network with the same degree distribution would have. It puts a number on how community-like a partition actually is.
So the goal becomes finding the network division that gives the highest possible Q score.
That's the idea for many algorithms. Maximize modularity. Now, one of the earliest and most influential algorithms here, though it wasn't directly optimizing Q initially, was the Girvan-Newman algorithm.
Girvan-Newman. That name comes up a lot.
It does. It's a divisive hierarchical approach, like we talked about, but its splitting criterion is based on something called edge-betweenness centrality.
Edge-betweenness. So it's about finding the bridges between communities.
That's a perfect way to think about it. Imagine a city's road network again. Edge-betweenness is like identifying the most critical bridges or the main arteries.
The ones everyone has to use.
Exactly. The links that lie on the highest number of shortest paths between all pairs of nodes in the network. Links acting as bridges between distinct communities will naturally have very high betweenness because many paths have to cross them to get from one side to the other. So the Girvan-Newman algorithm iteratively finds the link with the highest betweenness score and removes it. Then it recalculates all the betweenness scores.
Recalculates each time.
Yes, that's the costly part. And it removes the next highest, and so on. This progressively breaks the network apart, revealing the community structure as components become disconnected. It forms a hierarchy of partitions.
You mentioned this iterative removal breaks the network. Are there famous examples where this method worked particularly well, maybe a benchmark network?
Absolutely. The classic example is Zachary's Karate Club network. It's legendary in this field.
The Karate Club.
Yeah, it models the social ties within a university karate club that famously split into two factions after a real-world conflict between the instructor and the club president.
So there was a known ground truth split.
Exactly. And the Girvan-Newman algorithm is actually quite good at detecting this real-world division based purely on the network structure, sometimes with a few minor misclassifications, but generally it finds the split.
So the key insight wasn't just finding groups, but finding these critical links.
That's a huge part of it. It exposes the vulnerability points of the network. Understanding these high betweenness links is like finding the linchpin of a system. Remove it, and the structure might fragment. It teaches us about network resilience or fragility.
But you mentioned it's costly.
Yes, that's its main drawback. Recalculating betweenness after every single edge removal is computationally very expensive.
Yeah.
It makes it impractical for really large networks, maybe networks over 10,000 nodes or so. It starts to become infeasible.
That scalability problem sounds like a major hurdle for applying this to, say, large social networks or the web. How did researchers get around that?
Well, that brings us to methods that more directly optimize modularity and do it much faster. And the king of the hill there is probably the Louvain algorithm.
Louvain, yes, I've definitely heard that name. How does it manage to be so fast?
The Louvain algorithm is really quite clever. It's a fast agglomerative procedure, so bottom up, and it works in 2 steps that get repeated.
Okay, 2 steps.
First step, it starts with each node in its own little community. Then it goes through each node one by one and considers moving it to the community of one of its neighbors. It calculates the change in modularity Q for each possible move.
Okay.
It makes the move that gives the biggest increase in Q. It keeps doing this for all nodes, iterating, until no single node move can improve the overall modularity score anymore.
Okay, so a local optimization phase. What's the second step?
This is the ingenious part. Once that first phase stabilizes, it takes each of the communities just formed and collapses each one down into a single supernode.
It builds a network of communities.
Exactly. It creates a new, smaller, weighted network.
Right.
The weight of a link between 2 supernodes is the sum of the weights of the links between the original nodes in those 2 communities. And links within an original community become self-loops on the supernode.
That shrinks the network significantly.
Massively. And then it just repeats the whole process. Step 1, on the supernode network, finding the best moves for the supernodes. Then step 2, aggregating those communities into even bigger supernodes.
Wow.
This repeats, shrinking the network dramatically at each stage, allowing for incredibly swift calculations. The real aha moment with Louvain wasn't just speed, though. It's that it made community detection practical for the massive networks we deal with today. Social media, global trade, biological networks.
It unlocked the ability to analyze real-world scale.
Precisely. It took community detection from being a neat academic idea to being an indispensable tool for understanding complex systems.
That's a fantastic solution for scalability, but is modularity, even optimized efficiently by Louvain, a perfect metric? Does it have any blind spots?
That's a really important question, and no, it's not perfect. Modularity, for all its power, has an intrinsic issue known as the resolution limit.
Resolution.
Yeah. It means that modularity optimization can sometimes fail to detect small but very real and tightly knit communities, especially if the total number of internal links within that small community falls below a certain threshold relative to the whole network size.
So it might merge small, obvious groups together.
It can, yes. Imagine a network that's actually made of many small, very dense cliques groups where everyone is connected to everyone else. Modularity optimization might actually merge several of these cliques into one larger, less natural community, simply because doing so gives a slightly higher overall Q score for the entire network partition.
Huh. Why would it do that?
Because Q compares internal density to what's expected in a random network of the same total size and degree distribution. Sometimes grouping small, dense things together looks slightly better against that random baseline than keeping them separate, even if they feel like distinct units to us.
So the resolution limit isn't really a flaw, more like a feature of what it measures.
That's a good way to put it. It's a fundamental reminder that our notion of a community is often scale-dependent. A small research team is a community, but in the context of the entire global scientific network, it might be too small for standard modularity to see it clearly unless you adjust things.
How do you adjust?
Well, to mitigate this, researchers often introduce a resolution parameter into the modularity equation. It lets you effectively tune the scale you're looking at, kind of like zooming in or out.
Okay, so you can tweak it. But if modularity has this inherent scale issue, are there completely different ways to think about finding communities?
Yes, there are. Besides tweaking modularity, there's a fundamentally different approach rooted in statistical inference. The main tools here are stochastic block models, or SBMs.
Stochastic block models. Sounds statistical.
It is. The basic idea is quite elegant, actually. You assume the nodes are divided into some number of groups, or blocks, and then the probability of a connection existing between any 2 nodes depends only on which blocks those 2 nodes belong to.
Only on their group membership, not on the individual nodes themselves.
In the simplest SBM, yes. All nodes within the same block are treated as statistically equivalent in terms of their connection patterns to other blocks. These probabilities The chance of a link between block A and block B or within block A form a small matrix, the stochastic block matrix.
So this model isn't just for finding those typical dense communities then?
Not at all. That's its power. While it can generate classic community structures where the probability of links within a block is much higher than between blocks, it's far more versatile. It can generate disassortative structures where links are more likely between different blocks. Think of maybe predator-prey relationships, or multipartite networks where links only exist between certain types of blocks, or even those core periphery structures we might talk about later.
Okay, much more flexible.
For real networks, where nodes definitely aren't all the same, a more sophisticated version called the degree-corrected stochastic block model, or DCSBM, is often used. It accounts for the fact that different nodes have vastly different numbers of connections, degrees.
How does it find the groups then?
It's about inference. Given an observed network, you try to find the partition of nodes into blocks and the block matrix probabilities that make it most likely that this specific SBM could have generated the network you actually see. It's maximizing a likelihood function.
So it's finding the underlying generative process.
Exactly. Less about just finding density patterns and more about uncovering the statistical rules that likely govern how the network was formed.
And I recall reading that M.E.J. Newman, a big name in this field, made a connection between modularity and SBMs back in 2016.
Yes, that was a really crucial piece of work. Newman showed a mathematical equivalence between optimizing a generalized version of modularity, one that includes that resolution parameter we talked about, and using maximum likelihood methods to fit a specific type of SBM, the degree-corrected planted partition model.
What did that mean practically?
It provided a much more solid theoretical foundation for modularity. It showed that maximizing modularity with the resolution parameter is essentially equivalent to assuming the network was generated by a specific kind of block model and finding the best fit. It clarifies the statistical assumptions hidden inside modularity optimization. It was a really nice unification.
Okay, so we have modularity SBMs, but not all network structures fit neatly into those distinct non-overlapping community boxes, right? Sometimes we see things like core periphery. What's that structure about?
Right. If we connect this to the bigger picture, core periphery is another important mesoscale structure. It describes networks that have a dense, highly interconnected core of nodes, often the high-degree hubs.
The popular kids.
Sort of, yeah. And then a periphery of nodes that are much less connected to each other, but connect frequently into the core. Think of a star network, but with the center being a whole cluster of nodes instead of just one.
Like a city center versus the suburbs.
That's a great visual.
Yeah.
The bustling city center is the core, highly connected within itself. The quieter suburbs are the periphery, fewer connections amongst themselves, but lots of roads leading into the core. Social networks can sometimes show this, especially if high-degree nodes tend to connect to other high-degree nodes, what we call assortative mixing.
And how do we actually pinpoint which nodes are core and which are periphery?
There are several ways, actually. Some methods focus on edge density, defining a core score for each node, and optimizing some function to separate core from periphery.
Okay.
Others look at network function, like transport properties. There's a path score method that measures how often a node lies on alternative optimal paths if the main shortest path is disrupted. Nodes crucial for resilience might be considered core.
Interesting, like key backup roads.
Exactly. Then there are spectral methods, using linear algebra on the network's matrices. And a more straightforward approach, often used just for visualization or filtering, is K-core decomposition.
K-core, how does that work?
It's pretty intuitive. You iteratively peel away nodes with low degree. First, remove all nodes with degree 1, then recalculate degrees, and remove all nodes that now have degree 1. Keep going. Then remove all nodes with degree 2 or less, recalculate, repeat, and so on. What's left after you've peeled off nodes with degree less than k is the co-core. The innermost, highest co-core represents the most densely interconnected part of the network. It's a great way to just filter out the periphery and see the network's heart.
Okay, that makes sense. Now, another bit of messiness in real networks is overlapping communities. We all belong to multiple groups, right? Family, work, hobbies.
Absolutely.
But traditional community detection, like we've mostly discussed, often forces each node into just one community. That feels unrealistic.
It is unrealistic for many, many systems. And this is a major challenge for those traditional methods. Pervasive overlap, where nodes belong strongly to multiple groups, can even break that fundamental assumption that communities have more internal than external links, because a node's links might be split across several groups it belongs to.
Because the focus was always on grouping the nodes.
Exactly. The traditional view partitions the set of nodes into exclusive boxes.
But I understand there's a different way to think about this, a shift in perspective.
Indeed. And it's quite elegant. It's called link communities.
Link communities, so grouping the connections, not the nodes.
Precisely. Instead of grouping nodes, this approach defines communities as groups of links. The underlying idea is this. While a person, a node, clearly belongs to multiple social circles, a specific relationship, a link, say between two colleagues, often exists for one dominant reason: they work together.
Ah, the link itself has a primary context.
Often, yes. So by assigning each link to a single community, nodes can naturally inherit multiple memberships. A node belongs to all the link communities associated with its connections. This allows for inherent overlap without forcing nodes into single categories.
How do you find these link communities?
It typically uses hierarchical clustering again, but this time the similarity is measured between links, for example, based on the shared neighbors of the nodes they connect. And the quality of the partition is evaluated using something called partition density, which, very importantly, does not suffer from the resolution limit that modularity has.
That's a really interesting reframing, focusing on the relationships themselves. Is there a good example where this reveals something new?
A great illustration comes from word association networks. Think about the word Newton.
Okay. Isaac Newton.
Right. If you build a network of words associated with Newton, linked communities could correctly identify distinct groups of links. Maybe one group representing science concepts, physics, gravity, calculus, another representing intellect, genius, smart, maybe another related to apple or wheat, Fig Newton.
Right.
The node Newton itself would then naturally belong to all of these linked communities, reflecting its multiple meanings and associations. It captures the polysemy.
That makes perfect sense.
And quantitative studies comparing linked communities to traditional node communities on real-world networks, things like Amazon product co-purchasing networks, metabolic networks, co-team interactions, often show the linked communities reveal more meaningful structure related to the network's metadata, especially when there's lots of overlap.
So a powerful alternative, especially for complex overlapping systems. Okay, we've covered a lot of ground, different ways to define communities, algorithms to find them, metrics to evaluate them, even these more complex structures. How do we actually know if any of these methods are working well? How do we benchmark them?
That's critical, right? We need ways to test these algorithms. We use benchmarks. These can be artificial benchmarks, synthetic networks, where we know the community structure because we built it in.
We clamp the answer.
Exactly. Like those stochastic plot models we discussed. A special, simpler case is the planted partition model. You create a network with a specific number of communities, maybe all the same size, and you set the probability of links forming within communities, call it pint, higher than the probability between communities, pext.
So you control how hard the problem is.
Precisely. You can make the communities really obvious, high pint, low pext, or really fuzzy and hard to find.
And the famous GN benchmark, that's one of these.
Yes. The Girvan-Newman GN benchmark is a specific recipe using the planted partition model. Usually 128 nodes, 4 communities, average degree of 16. Researchers use it to test algorithms by varying those probabilities.
But real networks aren't usually that neat, are they?
No, that's the limitation. Real networks usually have very diverse node degrees, some hubs, lots of low-degree nodes, and communities of wildly different sizes. The GN benchmark is too uniform.
So what's used for more realism?
For more realistic artificial tests, the LFR benchmark is now commonly used. It generates networks that have heavy tail distributions for both node degrees and community sizes, mimicking real-world properties much better. We also use negative tests.
Negative tests.
Yeah, you generate a purely random network where there shouldn't be any community structure. A good algorithm shouldn't find strong communities in random noise. It's a sanity check.
Okay, that makes sense. What about benchmarks based on real-world data?
Those are real benchmarks. These are networks where we have some external information, some ground truth, suggesting a likely community structure.
Like the karate club again.
Exactly. Zachary's Karate Club is the most famous real benchmark because the split was documented sociologically. Other examples might be, say, a power grid network, where communities might reflect geographical regions.
Right.
Or biological networks where known functional modules exist. For these, we run our algorithm, get a partition, and then compare it to the known ground truth.
How do you compare the detected structure to the ground truth?
We use quantitative metrics. A very common one is normalized mutual information, or NMI. It measures the statistical similarity between two partitions. A score of 1 means the detected partition perfectly matches the ground truth. A score of 0 means they're completely independent, no better than random guessing.
So NMI gives a score for accuracy on real benchmarks.
Precisely. It helps us objectively compare how well different algorithms perform when we have some idea of the right answer.
Wow. What a journey through this intricate world of network communities. From just defining what a community is, exploring algorithms like Gerben, Newman, and Louvain, maximizing modularity, dealing with resolution limits.
Right, and then into SPMs, core periphery structures, and the whole overlapping community problem tackled by linked communities.
It really shows how these tools help us uncover hidden patterns in everything from, brain functions to social dynamics online.
It absolutely highlights how crucial understanding these mesoscale structures bigger than nodes but smaller than the whole network, is for really comprehending how complex systems function and behave all around us.
It really does, from disease spread, information flow, biological processes. These groupings are fundamental. And it makes you think, doesn't it? Even with all these sophisticated algorithms and metrics, the very definition of a community can still feel a bit fluid, context-dependent. It pushes us to keep refining how we see organization and complexity.
Absolutely. There's often not one single true community structure, but different structures visible at different scales or through different lenses.
So maybe a final thought for our listeners. What kind of community are you a part of, online or offline? And what really defines its boundaries?
Okay, so have you ever noticed how some ideas just explode, spreading like wildfire, while others just fizzle out?
Yeah, totally. Or think about trends, how they can sweep through almost overnight. It's almost like watching a disease spread in a way.
Exactly. Well, today we're doing a deep dive into exactly that, the fascinating world of dynamics on networks.
And what's really compelling here, I think, is how the actual structure of our connections could be online friends, work colleagues, even just who lives near you. How that structure really dictates how fast and how far things like information or influence or even, infections actually spread.
Right.
So our mission today is sort of uncover how these forces work, how they drive growth or change within all sorts of systems. We want to give you a shortcut maybe to understanding these invisible engines shaping our world.
And we've gathered some really insightful sources for this, academic lectures on network science, papers looking at everything from opinion formation to like quarantine strategies.
Lots to dig into.
Definitely. So you should get ready for some aha moments, hopefully.
Yeah.
So when we talk about dynamics on networks, we're not just talking about the networks themselves, like how they exist.
No, it's about movement.
It's about how things move, how they change across those connections. It's like studying the forces, the properties that make things grow or develop or shift within any connected system.
And those nodes we mentioned, just think of them as the points in the network. Could be a person, a computer, a city, anything that connects, really.
Right.
And this immediately makes you ask, okay, why does this matter to me right now?
Yeah, the practical side.
Well, think about something like misinformation. It's everywhere. One of our sources has this really striking example from the 2016 U.S. election. There was this completely false news report alleging some really out there stuff, satanic rituals, by a candidate's staff, and it just went viral on Twitter.
Wow. And how did it spread? Was it random?
Not at all. It primarily moved among supporters of the opposing candidate, people who were kind of primed to believe stories that fit their existing views, you know?
That makes sense. Confirmation bias in action.
Exactly. And here's the kicker. Automated accounts, social bots, they played a huge role in amplifying it, pushing it out there far wider than it might have gone otherwise.
So not just organic sharing.
No, definitely not just organic. And this wasn't a one-off thing. It was one of thousands of similar stories circulating back then. Experts think it influenced opinions, maybe even affected the election results.
It's pretty stark, isn't it? Network scientists study this stuff because the structure, the actual shape of these online social networks is key to how messages go viral. You see those influential nodes, including the bots, having disproportionate power.
It really shows how our connections can make us vulnerable, yeah. But also, understanding the mechanics gives us a way to potentially counteract it, or at least be aware.
Okay, so that's information diffusion, like fake news. But that's just one type of dynamic process, right?
Oh yeah, just one class. Let's dig a bit deeper into how ideas and influence, more generally, move through these networks.
Okay. Well, Our sources bring up this concept called the fractional threshold model. And this one feels pretty intuitive, actually. Think about trying a new snack. There was this example, honey butter chips, in the material. Maybe you think, okay, if 40% of my friends try it, I'm in.
But I might need more convincing. Maybe I need like 90% of my friends to be raving about it before I buy a bag.
Exactly. Everyone has a different personal threshold for jumping on board, for being activated. It depends on who you're connected to.
Precisely. The model shows an inactive node. A person becomes active if a certain fraction of their neighbors are already active. And what's really cool, mathematically speaking...
Uh-oh, math incoming.
Just a little. Even a simple analysis shows this potential for a phase transition, like water suddenly turning to steam.
Right, a sudden shift.
Yeah. In networks, it means an idea or a trend can go from barely moving to suddenly exploding very quickly once enough people cross their thresholds. But then, maybe surprisingly, it can also peak and start to decline after that explosive growth.
So it's not just gradual spread. There can be these tipping points.
Exactly. Tipping points driven by individual thresholds and network structure.
And it suggests there are these subtle leverage points, right? Where maybe just a few early adopters, if they're the right ones, can trigger this massive shift.
Or you can see when a trend is about to hit that critical mass.
And it's not just how many people around you adopt something, but who they are, which connects to that classic idea from Mark Granovetter.
Ah, yes. The strength of weak ties. Foundational stuff.
Explain that a bit. What's the difference between strong and weak ties?
So Granovetter distinguishes between them. Strong ties are usually your close friends, family, the people you're really tight with. They give emotional support, often reinforce what you already think.
Your echo chamber, maybe.
Sometimes, yeah. Weak ties, on the other hand, are your acquaintances, people you know but aren't super close to. Maybe colleagues in other departments, friends of friends. And these connections, the weak ties, are often the source of genuinely new information. Things you wouldn't hear from your inner circle. Granovetter famously said, basically, hit up the friends you don't usually talk to if you want brand new info.
So those weaker links can be surprisingly powerful for spreading novel ideas or opportunities. Stuff that gets stuck in the echo chamber otherwise.
Exactly. They bridge different groups. Super important.
Okay, so from ideas, let's shift gears to something more, well, literal. Epidemics.
A very clear and often scary example of network dynamics.
Yeah, the sources use some powerful visuals. You could almost picture those maps showing the Black Death arriving in Europe, 1346, and then just spreading across the whole continent in just a few years.
It's a chilling historical example of how connected places were even then and how devastating the consequences could be.
And much more recently, we all lived through the start of COVID-19.
Absolutely. The material even had that headline from BBC News Korea, March 2020, COVID-19, who now Europe is the center of the global COVID-19 epidemic.
Really brings home the urgency, doesn't it? Studying how diseases spread on networks isn't just academic.
Not at all. It's critical for public health.
So how do scientists model this? Our sources mentioned a few different models, SI, SIS.
Right, there's a progression. The simplest is SI, susceptible infected. Once you're infected, you stay infected. Then SIS, susceptible infected, susceptible, where you can recover but then become susceptible again, like with some colds.
Okay.
Then SIR, susceptible, infected, recovered, where recovery means you're immune or removed from the pool, maybe through death, unfortunately. And SIRS, where recovery gives only temporary immunity and you can become susceptible again later.
And these models track the fractions.
Right.
The percentage of people in each state over time.
Exactly. They use equations to see how those proportions change, giving different perspectives on how a disease may play out.
And one key finding is this idea of a critical point.
Yes, that's huge. In many standard network types, an infection needs a certain push, a minimum level of transmission before it really takes off and becomes an epidemic. Below that threshold, it might just die out.
But not always.
Not always. This is where it gets really interesting with certain network structures. Specifically, scale-free networks. These are networks that have a few nodes with a massive number of connections, think major airline hubs or super popular accounts on social media.
The hubs.
Right. In these scale-free networks, researchers found there's often an absence of that critical point. Spreading can basically always happen, even if the initial infection rate is tiny.
Why? Because those hubs get infected and just blasted out everywhere.
Precisely. They act as superspreaders, constantly reinfecting the network, making containment incredibly difficult. It means strategies have to be different for those kinds of networks.
Which links directly to public health strategy, right?
Yeah.
Like the K-quarantine model mentioned for COVID-19, based on South Korea's approach.
Exactly, a fantastic real-world application. Instead of locking everything down, they used a more targeted approach, local quarantine, focused around confirmed patients. It's network thinking in action.
How did that model work, technically?
Well, it used a SARE framework that's susceptible, exposed, meaning infected but not yet infectious, infected, and recovered. But crucially, it modeled link dynamics.
Link dynamics, meaning connections change.
Yes. Connections to people who were infected and isolated were treated as temporarily cut from the network. Then, when they were released, those links were reinstated.
So the network itself was changing in response to the quarantine.
Right. Which leads to a reproduction number, how many people each infected person infects, that changes over time. The simulations using this showed something interesting. A lot of asymptomatic cases were actually caught because they were quarantined alongside confirmed cases they'd been in contact with.
Wow. So it was effective at catching hidden spreaders.
It seems so. It was a sophisticated attempt to balance controlling the spread with minimizing the economic disruption. A real testament to applying network science in a crisis.
And all these models and strategies, they rely on some pretty complex math underneath, don't they? The sources mentioned mean field models and moment closure. Sounds intense.
It is a bit technical, yeah. Essentially, those are methods scientists use to simplify the incredibly complex reality of a network. You can't track every single interaction perfectly.
You approximate.
You approximate. You try to boil it down to a smaller set of equations that capture the main dynamics. It helps identify overall patterns, potential biases in simpler models, especially in networks that have lots of short loops or cycles. It's about making the complexity manageable enough to get useful insights.
Okay, complexity managed. Let's shift again from pathogens to perceptions, opinion dynamics.
Right, how ideas and beliefs spread and evolve. This is critical because opinions drive behavior, influence policy, and they're constantly being shaped, sometimes manipulated, especially on social media.
And the models here are similar to the influence models we talked about earlier.
Similar, yes, but with distinct features. Often you're dealing with discrete opinions, like clear choices.
Yeah.
Yes, no, buy, sell, political, left, right.
Or sometimes continuous ones.
Or continuous, exactly. Like how strongly you agree with something on a scale or your preference level.
So how do these models typically work?
Usually you start by assigning opinions randomly across the network nodes. So, initial disagreement. Then you apply an opinion update rule over and over. People interact, maybe change their minds based on their neighbors.
And what happens? Does everyone end up agreeing?
It depends. The system might reach a steady state. That could be consensus, where everyone eventually holds the same opinion. Or it could be polarization, where opinions split into distinct, stable camps. Or sometimes it never really settles down. Opinions keep fluctuating, though maybe some average features stay consistent. It's a dynamic process.
Okay. What are some common update rules? The sources mentioned a couple.
Two big ones for discrete opinions are the majority model and the voter model.
Majority model sounds straightforward. You adopt the opinion held by most of your neighbors.
Pretty much. If more of your connections think X than Y, you switch to X. What's interesting is that this often leads to coexistence, different opinions surviving in different parts of the network. Getting full consensus usually only happens on really simple network structures, like a simple line or grid.
Okay, so the majority doesn't always wipe out the minority. What about the voter model? That sounds different.
It is quite different. In the voter model, a node doesn't look at all its neighbors. It randomly picks just one neighbor.
Just one?
Just one, and adopts that neighbor's opinion, whatever it is.
Huh. That seems almost random. Like it wouldn't lead anywhere specific.
It feels random at the individual level, yes. But what's fascinating is that if you average it out over many runs, or look at the long-term behavior, it often does lead to consensus.
Really? Even if an opinion starts as a minority?
Even then. That minority opinion can, through this random neighbor copying process, eventually take over the entire network. It shows how persistent, even seemingly random, exposure can be incredibly powerful, maybe more so than overt majority pressure sometimes.
That is fascinating. Okay, so opinion spread on networks. But then you mentioned something even more complex. They can change the networks too.
Yes. This is the idea of co-evolution of networks and opinions. It's not just information flowing on static train tracks. The tracks themselves are changing based on the cargo.
Your beliefs influence who you connect with, and who you connect with influences your beliefs.
Like a feedback loop.
Exactly like a feedback loop.
Yeah.
Or, as you said earlier, a dance. There's a really elegant model by Peter Holm and Emmy Jane Newman that captures this dance.
How does it work?
It involves a parameter, let's call it P, which balances two things happening. With probability P, a node looks at its connections and says, this neighbor disagrees with me. So it cuts that tie and randomly forms a new connection with someone else in the network who shares its opinion. So actively seeking out agreement, rewiring your network to match your views.
Right. That's the network changing. Then, with the remaining probability, 1p, the node doesn't change its connections. Instead, it just does what the voter model does, picks a neighbor and adopts their opinion.
So changing your opinion to match your existing friends.
Precisely. You're either changing friends to match opinions or opinions to match friends.
And what does this model show? What happens as you adjust that balance P?
It shows another phase transition. As P changes, as the tendency to rewire your network versus changing your mind shifts, the whole system can flip. It can go from a state with diverse opinions coexisting to a state where one opinion dominates and most people agree.
So the balance between social adaptation and belief adaptation is crucial for whether a society becomes uniform or stays diverse.
That's what it suggests. It shows how this interplay can drive convergence or maintain separation.
So what if one process is way faster than the other? Like if opinions change really easily, but we're slow to change our friend groups, or the other way around.
Great question. The sources looked into that too. If opinion convergence is much faster than network evolution, so beliefs shift quickly, but connections are sticky, you tend to get a giant component of consensus, a big block of agreement forms.
That's okay. And the opposite. If we change friends easily, but our opinions are stubborn?
If opinion convergence is much slower than network evolution, connections rewire rapidly, but beliefs are hard to change, it tends to lead to fragmented components. The network breaks up into separate groups that persistently disagree.
Wow. So the relative speeds really matter for social cohesion or fragmentation.
Absolutely. It highlights this delicate balance between how flexible our beliefs are and how fluid our social ties are.
Incredible. We've really covered a lot of ground from fake news spreading to epidemics to how our own opinions form and even reshape our social world. It's pretty eye-opening to see how these abstract-sounding network models connect so directly to, well, everything.
It really is. And I think if you connect this to the bigger picture, understanding these dynamics gives you a really powerful framework. It helps you assess information more critically, maybe anticipate trends.
And even just recognize how your own network influences you.
All right.
Subtly,
Yeah.
or maybe not so subtly.
Exactly. In this age of just constant information coming at us, developing that critical thinking muscle, maybe informed by some of this network science way of thinking, it feels pretty essential.
I agree completely. And maybe that brings us to a final thought for you, our listener, kind of drawing on the spirit of network science itself. This deep dive we've taken today relies on the work of so many researchers, like the ones in our sources. It kind of stands on the shoulders of this huge interconnected body of knowledge, a giant component of understanding, you could say.
Nice pull on the term there.
Yeah, thanks. But it's a reminder, isn't it, that really understanding the world means appreciating how interconnected everything is, how it's all, in a way, networking.
Well said.
So maybe the question for you is, as you go about your day, what connections will you think about differently? Or what new piece of information might you seek out, consciously stepping outside your usual network pathways? What will you explore next?